This is lecture 5-2, review of rules of fractional and negative exponents, day 2. So we're still using all the rules on page 3 of your student note packet, but now we're on page 4 of the student note packet in the purple section. And we're going to go through the last set of review for fractional and negative exponents, and then we're moving on to logs. So ideally we solved these rules last year in Algebra 2, and this is just a really quick review of all of those rules that we need to know in order to apply them later on. Alrighty, so we've got example A looks like this. We're solving equations now. So this is where it gets a little bit more complicated. Again, I expect to see work shown for everything, for all those steps. So if you are showing no work, you're not going to get any credit on homework or the tests. So we want to solve for x here. In this case, x is in the exponent. So we got to see kind of where we can go. The first thing I think is easiest is if we put everything in its smallest base, and then we should see things kind of work out for us. So 27 can be expressed as 3 cubed, and 81 is 3 to the power 4. That's still being raised to the power 4, and then 3 to the power of 8, I can't change that. 3 is its smallest base. So now on the left-hand side, this becomes 3 to the power of 6x, and then this is 3 to the power of 16 times 3 to the power of 8. Now, rules of exponents tell us this. If we have the same base being multiplied, we can just add the exponents. So on the right-hand side, 16 plus 8 is just 24. And then once we've got both sides of the equation down to exactly the same base, rules of exponents tell us that we can just set the exponents equal to one another after that. So once I've got the bases the same on either side, and there's only one base, like we're not adding or subtracting or multiplying or dividing by another number, then we can just set those exponents equal to one another, and then I can solve for x. So x is equal to 4 here. Now, when we think about our final answers, think about what x originally was. X was an exponent. So our final answer here could have been negative. If we got a negative answer, that's okay. We just need to make sure that we think about what kind of values our final answers can be. All right, so for example B here, there's a couple of different ways you guys could think about approaching this. I think the easiest way is first to get everything in its smallest base, and then get rid of fractions, because I think dealing with fractions when we're solving equations of exponents is a little bit tricky. So 1 over 32, 32 can be rewritten as 2 to the power of 5, and then 16 is 2 to the power of 4. And then what I'm going to do on the left-hand side is I'm going to pull that 2 to the power of 5 to the numerator, and I'm going to express it as 2 to the power of negative 5, and that just gets rid of that fraction there that makes things a little bit more complicated. Okay, now I've got powers to powers on both the left and the right. We're just going to make sure that we multiply those powers together. So I'm always make sure you distribute everywhere, okay, when we're multiplying these things together. A lot of times people will forget to distribute to that second term. This is going to become 2 to the negative 5th plus 5x equal 2 to the 8x plus 12. Now we've got the left and right side down to a single base, and that is base 2. They're equal to one another. So here we can just drop the bases, set the exponents equal to one another, and then we can go about solving for x. So I'm going to get everything with an x on one side, everything without an x on the other side, and then just divide by 3. So x is equal to negative 17 over 3. Again, x was in the exponent. We can have negative exponents, so x can be negative. That is allowed. In the case of example C here, again, I'm just going to get everything into its smallest base and then go from there. Now, it doesn't necessarily have to work out to be the smallest base. In this case, 625, I can represent as 25 squared, or we could turn everything into base 5, as long as the bases are the same. So just kind of keep that in mind. Doesn't necessarily have to be the smallest base. Sometimes smallest bases just are easier to see. Okay, so in this case, 625 is conveniently 25 squared. So I don't need to go a step further and get those 25s into 5 squareds, because I can get the same base on both sides. Now to deal with that cube root, anytime we're taking roots, we can express roots as fractional exponents. That's a rule. So the square root is to the power of 1/2. The cube root would be raising something to the power of 1/3. The fourth root is raising something to the power of 1/4. So this becomes 25 squared over 3. Okay. okay, or 25 squared to the power of 1/3, and then we would multiply those things together. Once I've got the bases the same, in this case they're both 25, then I can set the exponents equal to one another. So in this case, x is equal to 2/3. Example D, I'm going to get 36 to 6 squared. This is over 6 to the 3x. I'm just going to distribute that 3 and or multiply the 3 and the x together. Now we've got this. So there's different ways we could go about doing this, okay? Here's the first way, and this is a little bit harder. First thing I'm going to do is, now I've got bases the same in the numerator and the denominator on the left-hand side. I know that I can combine these now by subtracting the exponents. Okay, so the left-hand side becomes 6 to the 2 minus 3x. But here's the problem. I don't have 6 as a base on the right-hand side. So right now, as it stands, I can't set the exponent on the left-hand side equal to anything because the bases aren't the same. However, if you can see this, we can represent 1 as anything raised to the power of 0. Once I've got bases the same on the left and the right, then I can set the exponents equal to one another. And then I can go about solving. In this case, x is equal to 2/3. Okay, that's one option. I'm going to go back to the top. I'm going to split off. Okay, the second option, option number 2, I could have cross-multiplied. All right, and what would have happened is that would have left me with 6 squared is equal to 1 times 6 to the 3x, or just 6 to the 3x. And I've got the bases the same now. I can set the exponents equal to one another, and we get the same answer. Both options are fine, they work. I think one is a little bit easier than the other. It's also a lot easier to see, I think, option number 2 than turning 1 into 6 to the power of 0. But take your pick. Okay, so then we move on to E, and E is a little bit trickier. So now x is no longer in the exponent. So we're not looking to get the bases the same on both sides and then set the exponents equal to one another, because we're solving for x now, and x is not in the exponent, it's actually a base itself. So I've got to figure out a different way to kind of manipulate things to get x by itself. The first thing we need to do is we need to figure out how to get rid of that power of 8, because what I don't want to do is I don't want to sit there and multiply 4 minus 2x times itself 8 times. That is not going to be helpful for us. We're not going to approach it that way. We want to use the rules of exponents in order to make solving this equation a little bit easier. So the way that I'm going to do that is very similar to the way that we get rid of a square. We take the square root. So in order to get rid of the power of 8, I'm going to take the 8th root, or I'm going to raise everything to the power of 1/8. And that leaves us with 4 minus 2x on the left-hand side, and 256 to the power of 1/8 on the right-hand side. Now, 256, that's not in its smallest base. 256 is 2 to the power of 8. That's being multiplied by 1/8. And so this kind of conveniently happens. 2 to the power of 8 to the power of 1/8. We multiply those exponents together, we're going to get 1. Now here's the deal. We're taking a root, and it's an even root. So if we're taking the square root of a number, you've got a positive or negative solution. We're taking an even root here. 1/8 is an even root. So we have positive and negative 2 as both of our options. So we don't want to forget those because we could get 2 different values for x. In this case, we are. So I'm going to have 4 minus 2x equal to positive 2, and 4 minus 2x equal to negative 2, and then I'm going to go about solving for x. So 2 different options because we took an even root. This is going to leave me with negative 2x equal to negative 2. X is equal to 1 in this case. And then over here, x is equal to positive 3. Okay, so 2 values there. X is the base, so we've got to approach it a little bit differently. Example F, we've got this hideous square root with a fraction on the inside. We're going to work on getting rid of that. So in order to get rid of a square root, which is raising something to the power of 1/2, we can just square both sides. I think that's the easiest and best first step. That's going to leave us with 2 to the 4x minus 7 over 32. is equal to 64 squared. And I'm going to leave it like that for just a minute. We're going to try and get this down to be a little bit easier to solve. Now, x in this case is an exponent. So we're solving for an exponent here, which means our goal is probably to get the bases the same on both the left and the right-hand side so that we can just get rid of the bases and set the exponents equal to one another. So I'm going to work on 32 and 64, getting those into smaller bases so we can apply some more rules of exponents. So 32 is 2 to the power of 5, and 64 is 2 to the power of 6, and then we're still raising that to the power of 2. So we have 2 to the 4x minus 7 over 2 to the 5th power is equal to 2 to the 12th power. And then there's a couple ways we could do this. I could apply on the left-hand side the rules of exponents that tell me that if the same bases are being divided, I can subtract the exponents. And then once I've got the bases the same on the left and the right, I can then combine like terms and set the exponents equal to one another. Okay, so 4x minus 12 is equal to 12. 4x is equal to 24, which means x is equal to 6 in this case. Option number 2, and I'll do this in a separate color, coming from that step, I could have cross multiplied, and this would become 2 to the power of 4x minus 7 is equal to 2 to the 5th times 2 to the 12th. And then that becomes 2. Because the bases are being multiplied, we add the exponents to the 17th power. And then we could set those exponents equal to one another. And then solve for x. Right? And we get the same answer. So that was option number 2. I think they're both about the same number of steps there. Take your pick on which one you like better. Our very final example of applying rules of exponents to solve equations comes in the form of example G. Again, in this case, x is in the exponents, so we're probably going to be looking to get the same base on the left and the right-hand side. I have this 5th root here, and the first thing I'm going to do is I'm just going to get rid of it. So to get rid of a 5th root, we raise everything to the power of 5. Same way we get rid of the square root, we raise everything to the power of 2. We're going to get rid of the 5th root by raising everything to the power of 5. And that is going to give us 25 to the power of x plus 22 over 5 to the power of 7 minus 24x. And then on the right-hand side, we've got 125 to the 5th power. All right, big numbers. I'm going to show some work to get everything kind of simplified here. So I'm going to get everything in its smallest base, and then we'll kind of go from there. Things should start to simplify. So 25 is 5 squared. Remember, that whole thing is being raised to the power of x plus 22. And then on the bottom in the denominator, we don't need to worry about simplifying anything. 125 is 5 cubed, and that's being raised to the power of 5 here. So what this becomes then, we remember to distribute that 2 to both of the terms there. In the numerator on the left-hand side, we get 5 to the 2x plus 44 over 5 to the 7 minus 24x. This is all equal to 5 to the 3 times 5, which is 15th power. All right, we're super close on getting the bases the same on the left and the right, so we can start setting everything, the exponents equal to one another. I am going to do one of two things. So one option here, this is number 1, is I can apply the rules of exponents when the bases are being divided. So that means I've got 5 to the power of 2x plus 44 minus the whole denominator power, 7 minus 24x. Now, the one thing we're going to want to make note of is that negative sign has to apply to both of the terms in the denominator. So just be careful on that. I see a lot of mistakes made on problems like this. That's equal to 5 to the 15th. And then once the bases are the same, we can just set the exponents equal to one another. I'm going to distribute that negative sign to get negative 7 plus 24x equal to 15. We can go about solving for x there. I'll do that in just a minute. Second option would be the cross-multiplying option. So that's going to leave me with 5 to the 2x plus 44 on the left-hand side. On the right-hand side, that's going to leave me with 5 to the 15th power times 5 to the 7 minus 24th x power. And then we can add those exponents together on the right-hand side. And then we can set the exponents equal to one another because the bases are the same. and solve for x. Okay? In any case, our final answer for x, we're going to be left with 26x's plus 37 is equal to 15 here. 26x is then equal to negative 22. So x is equal to negative 22 over 26, which is going to be negative 11 over 13. Okay, so two options. Take your pick on which one you like better, cross-multiplying or applying the rules of exponents with division of the same base. There you go. Make sure you guys are showing all of your work as you go through each of these steps.